8.2, rational exponents. So not to be confused with rational expressions, we're now talking about exponents as rationals. So up until now, we've seen the base of a number raised to a certain power, right? We call this an exponential expression, right? We're going to talk about these a little bit more, but today our exponent's going to be a rational number. So instead of nice easy things like 3 squared, we're going to have things like 3 to the half or 4 to the 2/3, right? Stuff like that. Hopefully you did the exponent review sheet. That'll help out a lot, right? So that you can remember all those exponent rules. Because luckily, remember that a rational number is just an integer, right? So, well, that's actually the other way around. An integer is just a rational number. So all of the integers play the same rules as the rationals, and therefore all the rationals play the same rules as the integers. So there's a few extra steps, right? 1 or 2, but other than that, it's essentially the same exponent rules over again. But let's take a look at them and how they work together. So let's consider forms of 1 over n. Okay, so n is going to be a natural number. So we're going to look at the things like 1/2, 1/3, 1/4, 1/5 first. Okay, so we're going to look at the numerator equal to 1. Okay, dot, 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 dot. Let's consider the comparison of these to radicals, okay, because it's going to make a lot of sense when you compare them to each other. But first, let's take a look at this example. Let's say I had 3 to the 1/2, right, and then I squared that. Well, that would be 3 to the 1/2 times itself. Remember, everything has to follow the same rules. So anything squared is that thing times itself, right? We can use our rules of exponents. If I have the same base, I add the exponents. Adding the exponents, I get 3 to the 1/2 plus 1/2. That's equal to 1. So it looks like 1/2 and 2 cancel to equal 1. In other words, we can use another exponent rule that says if I have a power to a power, right, I can multiply the powers times 2. That becomes, multiply the tops, multiply the bottoms, 3 to the 2 over 2, or again, 3 to the first. Right, so it obeys, even though one of them is irrational, it obeys exactly the same exponent rules. Power to power or product rule. Right, so same thing, same thing. Now let's consider this radical form. Consider this radical form. Let's consider that something we talked about last time. 3 squared, square rooted, right? 3 squared, square rooted. Well, from our last video and from our last class, hopefully you remember that any of the same power ends up canceling, right? Square roots are the opposite of squares, so these two end up canceling, and I also get a positive 3 for the principal root, right? So in other words, the square root of 3 is equal to 3 to the 1/2. That's exactly how it goes, okay? That's actually a definition, almost a definition of a radical. A radical and a rational, a definition of a rational exponent. Rational exponents are just radicals. It matches the index, so if the index is n, then the denominator is n. That's how it works. So if I had something like the cubed root of 5, then it would be 5 to the 1/3. It ends up in the denominator. If I had the 4th root of 16, then that would be 16 to the 1/4. Okay, so it ends up in the denominator. The denominator is the thing that's changing. 1 just ends up being power. Now remember, it's not the same thing as cubed, right? That's not our answer. We don't want to say it's the same thing as 5 cubed, because it's definitely not the same thing. The cubed root of 5 is going to be way smaller than 5 cubed, right? It's going to be 125 and something like, let's see, what is the cubed root of 5? Let's take a peek real fast. Cubed root of 5 is 1.7, so it's definitely not the same thing as 125. So it's to the 1/3. Excuse me. Alrighty. Here's some more examples for you down here. Let's see if we can change some of these guys into their radical form. Okay, so let's change some of these ones into their radical form. 64 to the 1/3. Well, my base is going to stay my radicand. Okay, so the base always stays the radicand. So this is still going to be a 64 underneath the radical sign. Okay, and then my fraction tells me my index. If this fraction is 1/3, then it must be the cubed root, 1 over 3, right? So that the index always matches the radicand, or sorry, the rational denominator. Let's try another one. Square root, well, I just gave it away. The fraction tells me that the index is going to be a 2, right? And I don't really need to write a 2 there. Remember, that's the lazy part. I just have a square root symbol. But if I wanted to just make this point super accurate, I could do that. And then my radicand is just my base. Radicand is my base, square root of 100. We could even simplify that to the principal root of 10, right? Maybe we can go back and simplify this to the principal root of 4. Not principal root, just root. Alright, let's keep going. Ooh, gotta be careful on this one. Gotta be careful. C and D are virtually identical except for some parentheses. Let's start with D, actually. So D takes the whole thing, negative 256, and the whole thing becomes the radicand. The whole thing becomes the radicand. And then my fraction tells me that this index must be 4, right? My 1 over 4 tells me the index has to be 4. So this would be not a real number, right? The answer to this would not be a real number because it's a negative under the radical. Can't have that when it's an even power. Comparing that to C, remember if there's no parentheses in front, then only the 256 ends up under the radicand, or is the radicand ends up under the radical. Still the same index, but the negative stays on the outside, and we arrive at the principal, or the negative root, the fourth root of 256 is 4. So we end up with negative 4. So since it's positive under here, I end up with a whole number. Right, I end up with a whole number. Okay. Not a whole number, pardon me. A negative number, an integer. Let's try that again with this one. Here I have negative 32 under the radical. So we can draw a radical symbol. The whole radicand is in parentheses, right? So it's negative 32. The whole base is in parentheses, so the radicand is the whole thing. And this would be an index of 5. And remember, it's only bad to have negatives under even roots, right? Because even things have to be positive. Even things have to be positive. This is an odd index. So there is, in fact, a number that when multiplied by itself 5 times equals negative 32. Oops. Negative 32. That number is negative 2. So odd indexes are okay. Even indexes, not a real number. Odd indexes are good. Alright, and one last one, right? We've got 1/8 to the 1/3. Once again, we can use our rules of exponents to maybe make this rational a little easier. So I've got 1 to the 1/3 over 8 to the 1/3, right? And that's the same thing as, if I convert them to radicals, cubed root of 1 over cubed root of 8. I could have switched them first, that would have been fine. And then we saw an example of this in the last section, right? If I had switched them first, I would have gotten, I would have instead seen this, cubed root of 1 over 8, since the whole thing is in the parentheses, the whole thing is the base, the whole thing becomes radicand. And then I would apply my product rule, my quotient rule, and I would have gotten the same thing. Would have gotten the same thing, right? And then I can actually take the cubed root of 1, that would be 1. The cubed root of 8 would be 2, and I can simplify to 1/2. So converting to radicals makes it fairly easy to solve, right? Makes it fairly easy to solve when you have things like 100, 256, 8, 32, right? The stuff that simplifies pretty easily. However, there is some validity in going back the other way. There is some ease of access. We saw that in kind of the first little mini example. If I'm doing stuff like squaring it, sometimes it's easier to take a radical or take a rational exponent than it is a radical because I just have to add 2 and 1, or I have to multiply 2 and 1/2, right? Instead of taking a radical. Or, for example, we could do it either way. We really could. You could do it either way. But it's up to you how you wanted to handle that. Going back and forth is pretty easy. Okay, when solving, so let's talk about a little larger powers of rational now. Not larger powers, but larger fractions. So we've talked about all the stuff with 1 in the numerator, right? The 1/3, the 1/2, the 1/4, right? But what about stuff like 2/3 or 4/9 or 125/64, right? What about that stuff? Well, those can definitely be exponents as well. Those bigger fractions, stuff with not 1 in the numerator, those can be exponents as well. We just treat them like a separate part. So take, for example, 2/3 here. If I wanted to find 8 to the 2/3, well, I can split it up using power of a power rule. So I can go backwards from using power of a power rule. Remember, power of a power rule says if you have, x to the 2 to the 3rd, right, that's equal to x to the 6th. So I can go backwards as well. I can split it up. We saw that when we were canceling radicals, right? We had things like x to the 12th as a radicand, and then a 3rd index, and we canceled them by changing it to x to the 4th to the 3rd. That was in the last section. We can do kind of the same thing with a rational. I have 8 to the 2/3. That's the same thing as 8 to the 1/3 twice, right? 8 to the 1/3 to the square. I recommend putting the 1/3 first instead of on the outside, but it really doesn't matter. At the end of the day, it's going to be the same thing. We're going to talk about that again in a sec. But you split it up so that the fraction part only has a numerator of 1. Once it has a numerator of 1, you can apply what we just talked about. You can form a radical. The cubed root of 8, right? The cubed root of 8. And then all of that would be squared. Simplify the radical part first, you get 2. And then you square it, you end up getting 4. Okay, so if 8 to the 2/3 would be 4. Awesome. That works for anything. Any fraction of m and n. Any denominator. I could do that with 125/64. I would get a to the 1/64 to the 125th, right? So you can just break it into 2 pieces. That's all you need to do. Just break it into 2 pieces. So let's try that. Let's see if we can evaluate some of these expressions with that idea. This one's pretty easy because the denominator the numerator, is still 1/2. It's just 1. The numerator is 1. So this just transfers into the square root of 36. Oh, and I have no idea why I wrote a 3 there when I even said the square root of 36. And since there's a negative in front, we know to take the principal root, so this would just be 6. Cool. That one was just a little reminder, I guess. 125 to the 2/3. Okay, this one's a little more complex. I'm going to split this up so I don't have to tackle both the 2 and the 3 at the same time. I'm going to write 125 to the 1/3 squared. Yeah, that's a lot of parentheses. Life goes on, right? Oh well. Now I'll tackle the inside first. That becomes the cubed root of 125, right? Convert. And I still got that squared on the outside. I know the cubed root of 125 is 5. So now I have 5 squared. And 5 squared is 25. 25. Awesome. So now I simplified this hideous looking thing into something nice and pretty. 25. Just had to go piece by piece. Well, let's try this one. -4 to the 5/2. Let's be super careful here. So -4 to the 5/2. So I've got -4 to the 1/2. Oops, no I don't. Yep, that's what I even said. Just be super careful, right? Notice there is no parentheses and I put parentheses in here. That's a bad idea. I don't want to do that. Instead, I'm just going to pull the parentheses out to the side and treat this like 4 to the 5/2. That's what I'm going to treat this like. So now, let's see, let's see, that would be 4 to the 1/2 to the 5th, right? Or negative square root of 4 to the 5th, which is negative of 2 to the 5th, right? Which would be negative 32. So negative 32 ends up being what -4 to the 5/2 would be. Awesome. Let's do another one. This one, much easier, or not easier, I should say. This one, I do not have to be as cautious because that negative is on the inside. The negative's on the inside. Still want to be cautious. Never want to be uncautious in a math problem. That's probably a poor choice of words. But I wouldn't make the same mistake that I just did, right? This one would be inside. So it would be -27, all of it to the 2/3 So I can split that up into 1/3 squared, right? So 1/3 and 2 instead of 2/3. Change that into, let's see, the cubed root of -27, which would be a problem if my index was not odd, right? It would be a problem if that was the square root of -27, because you can't have negative squared things, but you can have negative cubed things. You can have odd powers there. So that would be, let's see, -3 squared, and now that's equal to 9. And this example sort of shows you why it's kind of easier to take the cubed root first, because if I tried to square that, that might be a little hard, right? Might be a little hard. Or if I tried to put the square on the inside, I would get a really big number. So taking roots, getting things smaller first is just sort of an ease. It's an ease of problem kind of thing, an ease of access kind of thing. It's not really right or wrong, definitely not right or wrong. Like I'll show you right down here in a different color what happens if we did go the other route. So if I instead made this -27 squared to the 1/3, well, -27 squared, again, that's all in parentheses, -27 squared would be 729 to the 1/3. Notice my number just got really, really big, right? But it's okay, because I can still convert this to a radical. That would be the cubed root of 729. So instead, that would just be, I can still find the cubed root of 729. That would be totally easy to do. That again is equal to 9. So either way, we end up with the same answer, right? But if I didn't want to deal with a number like 729, then I would take the cubed root first and then deal with the squared root, right? And no matter, even if you did that on something like this or something like where you didn't have an answer, that would have ended up the same way. Okay. All right. Last one. -100 to the 3 halves. -100 to the 3 halves. Let's try that. So we're going to split it up. It's in parentheses, so that entire thing is to the 1/2 to the 3rd, right? Maybe we should do to the 3rd. No, that's okay. It's going to end up being the same. All right, so here we have square root of -100, all of that to the 3rd. And we run into a problem because this is even and -100, right? So there is no square root of -100. That's just not possible, right? I will prove to you that even if we went the other way, it would have ended up the same. -100 to the 3rd to the 1/2. That would end up being, let's see, -100 to the 3rd. -1, 2, 3, 4, 6, -1 million. 1 million to the 1/2, which would be the square root of that. And again, we end up with a negative under the radical. So either way, we ended up with no solution. This is not a negative root because there's no negative out in the front. If the parentheses hadn't been there, well, it would have been like problem C, right? We could have ended up with an answer with the negatives on the outside. But here, that's a problem because the negative is on the inside. So we just end up with no solution. Alrighty. So hopefully that cleared up some questions. The last thing we're going to talk about is a negative power in the exponent. So a -3/4. So instead of like 1/2 or 3/4, we're going to talk about things like -5/6. Okay? But like I said at the very beginning, the exponent rules follow exactly. So remember what the definition of a negative exponent is. If I have x to the -2, that's the same thing as 1 over x to the +2. Okay? So we're not changing the rules here just because they're rationals. Okay? We're just adding a few on because they're rationals, right? Because they do extra things. They're cooler. They're not changing the rules. They're just adding to the rules. They've got more gifts to them. So let's try out. So again, in general form, if you've got that, then you can take the whole thing under the denominator. Now be careful. The thing that people do a lot is switch the fraction in the in the exponent. Okay, this does not mean. Here, I'm going to write it a little easier to see. So what you do not want to do is make it a to the n over m. Okay, that is not the same thing. No, 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 no. Okay, what you want to do is flip the base. Flip the base, right? Over here, I didn't make that a 1/2 x to the 1/2. I made it a 1 over x squared, right? So the base becomes the fraction. So let's see how that looks with these problems down here. I've got 16 to the negative 3/4. That's technically 3 separate things to consider. I can rewrite this as 16 to the negative 1/4 to the third. That's 1, 2, 3 different rules here in a nice, easy, combined way. I'm going to start with the negative part. No, I'm not. Yeah, I am. I'm going to start with the negative part. So this becomes 1 over 16 to the 1/4 cubed. Starting with the fraction part, right? That becomes 1 over the 4th root of 16 cubed. That becomes 1 over 2 cubed. And lastly, it becomes 1 over 8. Notice I took care of 1, 2, 3 separate exponent parts, right? So it just did it in 3 separate steps. I didn't try to handle all 3 at the same time. Just handle in 3 separate steps. You end up with 1/8. Let's try another one. I've got 25 to the negative 3/2. 25 to the negative 3/2. So again, this is equal to 25 to the negative 1/2 to the third, right? Negative 1/2 to the third. Deal with the, I'll even show you, it doesn't matter which order you deal with this. Let's do this, let's make the outside one negative. So 1/2 to the negative third. There, I switched it up, right? I put the negative on the 3 instead of on the 1/2. Okay, cool. So now I will deal with this first. I have the square root of 25 to the negative third. That ends up being the principal root, right? Because it's positive, there's a negative front. So 5 to the negative third. Now I'll deal with the negative part, 1 over 5 to the third, or 1 over 125. There, works that way too, right? So you can take the negative on the fraction, you can put the negative on the whole number, right? You can put the negative on the denominator or the numerator is what I'm trying to say. Heck, you could deal with the negative last if you wanted to. You could deal with the whole number first. It's all, since it's all multiplication, it's all commutative. You can do whatever order you want. If you don't like dealing with fractions, deal with the radical part first, then deal with the negative exponent. Let's see what happens in C. All right, I've got 8 over 27 to the negative 2/3. 8 over 27 negative 2/3. I will consider this in a couple different steps. So I've got 8 over 27 to the, let's say, to the second, negative second, to the 1/3. So now this time I put the fraction on the outside. Okay, cool. And then we can distribute that negative. No, let's take the negative first. So that flips the fraction, 27 squared to the 1/3, right? So I took care of the negative first. I flipped the fraction. Then, whoops, I totally run out of room here. That's okay. I can make each one squared through distribution property. 27 squared, 729. So that would equal 729 over 8 squared is 64. 64. And that's all to the 1/3, right? Take the cubed root of each by distribution property. The cubed root of 729, I've done this like 3 times now and I still can't remember what it is. Okay, really? Sorry, my calculator decided to be silly for a second. The cubed root, 729, it's 9. Yeah, it's 9, I just remembered. So it would be 9 on the top. The cubed root of 64, that would be 4. We end up with 9/4. So again, it didn't matter what order. Just had to use the distribution property too this time, right? And we've seen examples of that. If you don't remember that one, go back and do the exponent worksheet. Distribution property says if you have something on to both the numerator and the denominator, you just distribute it to both. And the last one, 81 to the negative 3/2. Okay, so that would be 81 to the negative, we'll do 1/2. Let's not do it in red because the last one was in red. So that could be 81 to the negative 1/2 to the third. Again, I split it up into 3 separate pieces, right? The negative, the 1/2, and the third. Or, and the, yeah, to the third. So negative 81 would be, so 81 to the negative, right, would be 1 over 81 to the positive 1/2, not 2. 3. 1 over 81 to the 1/2 becomes 1 over the square root of 81, all that to the third. And then that equals 1 over, let's see, principal root here, 1 over 9 to the third. Now I distribute 1 over, that would be 729. 1 over 729 is my final answer. So it doesn't matter how you start, it's all commutative, right? But just deal with them in 3 separate pieces. Again, watch out for where exactly that negative is placed. If it's in the exponent, you are now making a fraction, right? If it is next to it, outside the parentheses, right, then it is still outside the parentheses. And if you have both, you must make the fraction and make it negative, right? So watch out for things like that, okay? Because those can get very easy to confuse where the negative goes and what will trip you up. Okay. Wow, lots of stuff done. Okay. Like I said before, all of the... Oh, so like I said before, it doesn't really matter. You can go whatever order you want, right? Whatever order satisfies it, go for it. You end up with the same answer either way. You can deal with the number first, or the numerator first, or the rational exponent first. You can deal with the negative first, right? It's up to you. And in general, that is the same for both, okay? It's the same for everything. Radicals and non-radicals. Okay. Let's convert between... Do we really need to do that? Let me just do this. Okay, so let's practice some converting between exponents and radicals. Okay, let's convert. We've seen these before. This would be the index of 2, square root of 13, right? Not a whole number, so I'm just going to leave it like that. Square root of 3, or square root of 9 would be 3, square root of 16 would be 4, so it's about 3 point something, but we're only going to leave it as a radical. 6 to the 3/4. Let's try that out. So 6 to the 1/4 to the third. That would be the 4th root of 6 to the third. And it says use the definition that takes the root first. So that's why I did take the root first. So if they ask you to take the root first, then make sure you take the root first, right? Make sure you take the root first. However, this is equal to the 4th root of 6 cubed. Same thing. The cube can go on the outside or the inside, but this is actually the answer they were looking for. All right, 9m to the 5/8. Be very careful that 5/8 is not applied to the 9, right? It's not in parentheses. So this one would just have a 9 on the outside. We would have m to the 1/8 to the 5th. So it'd be 9 square 8th root of m to the 5th. That would be our final answer. The 9 is on the outside. Compare it to this next one in D. Again, the 6 is on the outside. So this would be 6. See, the denominator is 3. And the x would be squared. Then it would be squared. Right? Minus. Now, the 4 is on the inside of the parentheses, right? So it's the whole thing to the 5/2. And I'm sort of skipping this writing it in 2 separate steps part because I feel like by now we should be able to jump from here to here, from the problem to here. If not, that's okay. You can still write it out with fractions. All right, always write it out with fractions if you need to. But I'm just going to make that jump. So this would be the 5th root of everything that's in parentheses, all of it to the 3rd. I take the root first, right? Let's keep going. We got some other variables now. R to the negative 2/3. Well, that would be R. So that would be 1 over something, right? Because of the negative. The cubed root of R squared. Cubed root of R squared. Let's make that 1 over part. Visible. So I took it piece by piece. I did it mentally, right? I said, okay, the negative means it's a fraction, right? The negative and the exponent. Then the denominator of 3 means it's a cubed root, and then the square just stays a squared, right? So now I just did it mentally. Again, if you're not there yet, that's fine. Just write it out on your paper. All right, over here. Last one, we've got a squared plus b squared. All of that underneath a radical of 1/2. So we got square root of a squared plus b squared. And we're going to pause right there, okay? I cannot simplify. This is not the nth root of a squared, okay? That's okay. We'll talk about it again a little later. But this does not equal a plus b, okay? It's the same thing as when you're distributing, okay? You can't distribute the 1/2 to each one of them, right? You cannot do that. So this is just what it looks like. That's the end of the day. Okay, so that's it. Cannot distribute 1/2 to both of those so that they cancel. Because you've got that addition sign in there. That addition just messes everything up. So it's just equal to square root of a squared plus b squared. PEMDAS gets in the way if you try to take it down to ab. Doesn't work, it's illegal, don't do it. Alrighty, so we've been dealing a lot with converting the rational into a radical, right? Converting the exponent into a radical. Let's go backwards now. Let's see if we can convert these guys to rational exponents, okay? So I've got this one, square root of 10. Recall if there's nothing there, it's a 2. So I keep the radicand becomes the base, and the index becomes a fraction, right? The index becomes a fraction. It's not negative, it's irrational. Let's look over here, do the same thing. The radicand becomes the base, right? Radicand becomes the base. And now I take it to a fraction. And this one I can simplify a little more. 3 to the 8 over 4, right? And then I can even simplify that. 8 over 4 would be 2. Even better, I can simplify that down to 9. But the main point is that the exponent stayed an exponent, the radical became a rational exponent, and then I could combine the two, right? I could combine the two. If I tried to solve this via radical form, I would have gotten the same answer, right? Because the 8 and the 4 would have canceled, or the 8 and the 8 and the 4 would have canceled, and I would be left with 2, and x3 squared would also be 9. Alright, let's try another one. Z to the 6 to the 6. Let's convert this first. I know some of you are thinking that's just z, and you're absolutely right, because of our nth root of nth power, right? They cancel each other out. But let's double check that it works another way. Let's convert this z to the 6th to the 1/6. That would be z to the 6 over 6. And indeed we still end up with z to the 1st. So if you weren't quite convinced on that nth power thing before, now you should be, because you can see it works with rationals as well. It works with a rational exponent as well. Alrighty, let's do one more. The cubed root of x times the cubed root of, times the square root of x. As this is, we wouldn't be able to do anything. Product rule, we'll talk about that a little later, but we can't combine these. There's no way to combine these as they are. However, if they were exponents, we might be able to combine them. So let's take these both to a base of x. And this one's going to be a 1/3. This one's going to be a 1/2. And yes, now we can combine them. They have a base, the same base. So this would be x to the 1/3 plus 1/2, right? Timesing, product rule, same base. 1/3 plus 1/2 is x to the, let's see, same bases would have to be 6. Then in order to get the first one to a 6, it'd be 2/6, the second one would be 3/6, and that's x to the 5/6. That would be our final answer. So you can combine them when they're exponents. You can't combine them when they're radicals. Interesting. It's just because that's not how a radical works. That's going to be very important in just a sec. Alright, so now we switched it back. So these two are very interchangeable, right? Because they are the same thing by definition. Alrighty, recall your exponent rules. They work the same for radicals. Here you've got the product rule, the negative exponent rule, the quotient rule, the distribution rule. Actually, that's distribution and negative put together. Here's the power of a power. Here's the distribution rule again, not in a quotient form, but in a product form. Here is it in a quotient form. And here is the negative exponent rule one more time. So, I think I accidentally wrote that twice. Oh, that's negative. Oh, sorry, that's the negative power rule. Negative power. That's not right. Ignore that. That's not even correct. That is the correct one. Yeah, don't do that. That's not a power rule. I'm going to delete that because that's not even right. Chances are this is already deleted in your notes, so you don't have to worry about it. Okay. Once again, as I've been saying this whole chapter, they apply for rationals and real numbers. They're the same thing. So let's go through and practice a couple of these using our exponent rules. So we have the same base here. That means product rule, right? Same base being multiplied, so we can make it over one base of 1/2 plus 1/4. Well, a half plus a fourth, that's going to be the same thing as 2/4 plus a fourth, right? And so we get 2 to the 3/4. That's our final answer. And you can leave the exponents. Remember, it's only finished if you have positive exponents. It doesn't say you have to have whole numbers. It says you have to have positive. This is positive, so we are done. Could convert it to a radical. Not necessary. Alright, looks like we got some quotient rule here. We got a lot of things going on here. So let's first convert. Okay, let's try this one. Now I know this one looks a little complicated. It's a complex fraction, but actually it's not even a complex fraction. We don't have fractions within fractions. We just have two of the same base being divided. So this is literally just straight up quotient rule. So I've got 5 to the 2/3 divided by 5 to the 7/3. In other words, that's 5 to the 2/3 minus 7/3, right? By quotient rule. Right here. Nope. No. Right there. 5 to the 2/3. So multiply or subtract the top from the bottom if they're being divided in the same base. So I can go ahead and do that. I end up getting 5 to the negative 5/3. Luckily, they already had the same base, so I could just subtract the tops, right? And I can't have any negative exponents, so I'll apply the negative exponent rule. 1/5 to the 5/3. And I have my answer. In other words, I have 2/3 on the top, 7/3 on the bottom. I cancel and have 5/3 on the bottom. Same thing as the cancellation version of the quotient rule as well. Alright, let's try another one. Here I can use distribution rule to start, right? So I get x to the 4/2, y to the 8/3 over y. Notice I'm multiplying fractions, so I just multiply the tops, multiply the bottoms. The bottom, quote unquote, for 4 is just going to be 4/1. So I didn't change any of the bottoms, I just changed the tops. And then I can reduce a little bit. 4/2 becomes x squared. 8/3 and 1. Let's see, I can subtract those. So I'll do that over here. So the base becomes y, well, I don't have to do it over there. Do it over here. Y to the 8/3 minus 1, right, by quotient rule. Let's see, 8/3 take away 1, or 3/3, leaves me with x squared y to the 5/3. And I'm done. All positive powers, one of each base. There's no more I can do. Let's do another one. I'm actually going to simplify within the parentheses first, then I'll apply the distribution rule. So within the parentheses, I see this negative exponent I can pull to the top. So I have x to the 4th, x squared. And then the y also can go down, so I have y to the 6th, y to the 1/3. All of that still being raised to the negative 2/3. I can use a little bit of product rule inside, so that's x to the 6th over, let's see, 6 converted to thirds would be 18/3, so not x. Y to the 19/3 on the bottom. All of that still being raised to the negative 2/3. Haven't done that yet. Alright, and that's about as simple as I can go. So I'm going to start with the negative 2/3 now. The negative part says I'm going to flip it. So I have y to the 19/3 to the x to the 6th, pardon me. Now that's to the positive 2/3, right? So I just took away that negative. And then I can use distribution rule. 2/3 times 19/3. Let's see, 2 times 19, I think it's 38. Yep, 38. So I get the y to the 38/9 over 2/3 times 6 would be x to the 12 over 3. And it looks like I can reduce that bottom one a little bit. So my final answer would be y to the 38 over 9 over x to the 4th. Not the prettiest fraction, 38 over 9, but that's okay. I have all positive exponents, and I have one of each base. I am done. Let's try one more. One more reducing. Alright, here I can use straight up distribution property, not distribution rule. I can just multiply that in, right? I can rainbow it in. I end up with m to the 3/4 times m to the 5/4. It is not going to be 2m to each of those powers, right? Because it's just like multiplying an m squared. You would multiply m squared to both of them, okay? So you're not suddenly ending up with 2. And then again, m to the 3/4 times m to the 1/4. That's the other one. So I just distributed in this first term, quote unquote. That looks like a 7, so I'm going to rewrite it. 3/4. Okay, now I can apply product rule to each of them. Let's see, that means I add the exponents, and luckily they are of the same base, so I end up with m to the 8/4, right? Over here, add them, I get m to the 4/4. Since they have the same denominator, I can add their numerators, and they're still being subtracted. I can reduce these both a little bit. That becomes 8 over 4 becomes 2, and 4 over 4 becomes 1. So I'm just left with m squared minus m, which are unlike terms. And so that's what I'm left with, m squared minus m. M squared minus m. Could factor a little bit if I wanted to. M times m minus 1. That would be fine. But that definitely does not equal m. If I had 2m minus m, that would be m. But this is m squared minus m, right? So that would be my final answer. Okie dokie. I don't know what I'm doing. Alrighty, so now we want to, the very last thing we're going to do today is simplify these expressions by writing them first in rational exponent form and then applying the rational exponents. Okay, so same thing. We got to make sure we end up with positives. Here we go. Again, so we've seen one example of something like this, right, where they have different radical indices and we can't do anything. So let's convert them to rational exponents first. This would be the, let's see, that index is going to be the denominator. That's going to stay a power. So x to the 2/3 is what that's going to become. This index is going to become a denominator, so times x to the 1/4. Notice how easy that conversion's getting. Hopefully, by this point, you can see that. If not, then go back to the beginning of this video and the last video and recheck it again, okay? That conversion should start getting a little more fluid as you go on, being able to convert back and forth between the two. Okay, so x to the 2/3 times x to the 1/4, that means you add them. 2/3 plus 1/4, that's product rule. Let's see, I need those both to be a common denominator. Whoops, forgot the x part. Need a common denominator, so 12 and 12. Let's see, to get that to be a 12, I had to times by 4, so to get that to be, so the 2 is now times by 4, or I get 8. That I needed to multiply by 3, so I get 3. Looks like it's equal to x. 8 plus 3 is 11/12. That is my final answer. Sweet. Let's go try B now. Let's convert first. So that, I'm going to write up here, the square root of x cubed, be careful, the square becomes the denominator. So this is to the 3/2 over, and this now, the 3 is the cubic, or the 3 is the index, so this would be x to the 2/3, right? So watch out for that. Watch out when you have multiples like this. Make sure you really think about, okay, the index has to be the radical. Or sorry, the index has to be the denominator. The index has to be the denominator. Whatever's under the radical, whatever the radicand is, that stays a power. Okay, cool. So now I've got this. This is the same thing as x to the 3/2 minus 2/3. That's the same thing, right? 3/2 minus 2/3. Okay, I need those both to be 6's so that they'll be in common. So x to the 6th oops, minus 6, right? In order to get this one to a 6, I had to multiply by 3, so I'll multiply by 3 on top. I get 9/6. Over here, I had to multiply by 2, so I'll multiply by 2 on top. I get 4/6. And I end up with x is equal to 5/6. Okay, easy peasy lemon squeezy, right? Let's do another one. Double radical, always fun. Let's convert one at a time. So let's start with the little radicand underneath. I've got z to the 1/4, right? Helps if I can actually write. So the little radicand is going to be z to the 1/4. And that still has another radical under it, right? Over it. That radical is now the squared, so right, because it's a 2 there, square root. So it's z to the 1/4 to the 1/2. And now we've got power rule. Z to the 1/4 times 1/2, it's going to be 1/8. And we're done. So don't panic if you see 2 radicals. It doesn't really mean anything. Just convert them to exponents. Okay, convert them to exponents. Exponents make your life easier. Let's do one more. Oh, excuse me. It's like 8 in the morning right now, so I'm exhausted. Yeah, my time's wrong, by the way. Okay. So square root of y, that converts to y to the 1/2, times, this whole thing is under the radical, so it's a whole thing is going to become the base, yz to the 1/3. Now I can use a little bit, so as they were, I could do nothing, right? Because they had different radicals, different radicands, pardon me. They had different radicands, I couldn't do anything. Now that they're exponents, I can use distribution rule and split up that second radicand, right? I can split up that second base. So I can get, first off, keep that y to the 1/2, but then this becomes y to the 1/3, oh, sorry about that, y to the 1/3, z to the 1/3. That's distribution rule because they're being multiplied, right? They're not being added, they're being multiplied. So I can distribute that as I see fit. And then I can combine the y's, 1/2 plus 1/3. We've done that already today. Where did it go? Yeah, we'll just do it again. It's good practice. So 1/2 plus 1/3, that's the same thing as y to the 3/6 plus 2/6. And still z to the 1/3. And we get y, totally running over, y to the 5/6, z to the 1/3 as our final answer. Y to the 5/6, z to the 1/3 is our final answer. Alrighty, so that's pretty much everything you'd ever want to know about rational exponents and converting between them and radicals. It's a lot to take in. Hopefully this answers most of your questions. If not, email me and I will see you in the next video.